Okay, James, take it away. Also, yes, sounds great.
Okay, I'm going to share my screen real quick. It only lets me share the entire desktop. That's fine. Does this work? Yeah. Everyone see this?
Yep.
Great. Hi, everybody. I'm James. I'm going to be talking a little bit about our thoughts on caching AOTAutograd. I've been working with Brian on this for a while now, and I'm still relatively new to this space, so if I get anything wrong or anything's inaccurate, please just let me know. And if you have any other questions, please interrupt me. But I wanted to just give an overview of our thoughts on this and how we're going to be approaching this, and then I have some open questions that we can discuss as well. So to start off, like the goals here are to improve our warm start compile times. So that means when one process like Qt2 starts compiling some input, and then we want to run it again on the same input, but maybe on a different process or maybe even in a different machine, we want to be able to cache that state. So we've already had efforts at this at levels lower than AOTAutograd. So we have Sam's FX graph cache, which caches the outputs of inductor. We have things like the Triton cache that Ozu was working on, which caches the compiled Triton binaries and executables. So this project is essentially just extending that work up one more level into AOTAutograd and figuring out what it would take in order to cache as much of the work that we do there as possible. So with any cache, the things we want to talk about here are computing a safe cache key and what exactly we're caching. What exactly are we serializing and saving in state? So we're going to start with computing the cache key here, and computing the cache key is probably going to be the most complicated part of this project because there's a lot of different moving parts that AOTAutograd depends on in order to like have correct behavior. So I've split these into a couple of categories. Things that are properties of the FX graph that Dynamo gives AOTAutograd, global configuration options, and then like state of the current like code base or like implementation state, and then extras that I haven't thought about because I'm sure there's plenty more. So the first category here are FX graph properties. So these are things that are on the FX graph or properties of the FX graph that we get passed in, or properties of any of the operators or functions within that FX graph. To think about these, we can kind of split these into a couple of categories. There are torch operators that are well-behaved. And when I say well-behaved here, I mean they include all of their information in the FX graph module itself, which means that as long as we can hash the FX graph, which there's existing work that we've already done with FX graph cache, which does this, where we like essentially pickle the text representation of the FX graph. These torch operators should behave well because they essentially have all their information right there, and we can just hash that information. A second category are higher order operators. So these usually have side tables and things that aren't apparent in the FX graph itself. And because of that, they are harder to handle because in order to generate a safe cache key, you would need to be able to know which parts of that side table are things that could affect the behavior of AOTAutograd. So for each higher order operation, we would have to think about a custom implementation for constructing a hash key that like works for FX graphs that contain these higher order ops. And then finally, there's a bunch of operators that aren't higher order ops, but also don't behave well. One example are like some detensor operations, which capture random state in their implementation, but those don't appear in the FX graph. They just like capture local variables in places based on how they're implemented. And this category is the more ambiguous one, where it's like we could try to think of every single one of these, but it's more likely that there are there's a set of these that it's more likely for there to be unknowns here where we don't necessarily know whether an operator like accidentally captures graph state in these ways. So the approach I think that makes most sense for this is to start with a set of operators that we know are well behaved, and cache only graph modules that work with those well behaved ones, and then looking at the models that we care about compiling and the models that and the use cases where caching is important, we'll be able to see which operators like don't fall into that category, and we'll want to implement like ways to cache those. And there's an interesting thing here about API design where we want to be able to construct a way for operators and in general properties of the FX graph to like designate how they want to be cached. Oz, you had a question? You're muted.
Sorry, not a question, but like a side note. For higher order operators, should we just require them to have like a survey functions, like serialize and deserialize functions, so that because like this has been becoming a challenge like multiple times so far, and if we require these like serialize, deserialize implementations for each of them, they will just behave like the rest of the well-behaved torch operators.
Yeah, Tugsu ran this by us before, and I think that's the right thing to do. One thing to note is that like being cacheable is not necessarily being serializable / deserializable. Like you could separate those out if we wanted, or we could just put those two concepts all together.
Yeah, theoretically, there could be things that affect serialization that do not affect whether it can be cached. Maybe. Yeah. Michael.
I have like a vague preference for kind of collapsing those two issues because we need to solve all these problems anyway, right? To serialize. So a logical thing to do would just be like serialize it and use that as the cache key if we have to solve that problem anyway. But I don't know if like, do we have examples of where those two things can maybe diverge?
Maybe it would be helpful if I could understand where are parts where we would want to be able to serialize the higher order op that aren't related to the caching. Like, are there other cases where we care about this, where it's like important to be able to do that? So
yeah, so we have like a different path where we like export the graph and serialize it,
right.
So that we can like move it around over the wire, whatever, and like publish it in various pieces of our infrastructure. So this is like the export flow, right? And so, you know, for a given higher order op, if we want to preserve that higher order op, we're going to have to, you know, make it serializable, right? And so we're going to run into this problem with, say, dtensor anyway. So I wonder if we can kind of just like kill two birds with one stone there. But yeah, so if, well, so Ed has a comment.
No, it's a different topic. So finish the thought.
Oh yeah, so I was just wondering, you know, like if it really is basically the same amount of work, right? Because you have to kind of make it well defined, make sure it's not closing over any unintentional state, etc. Then I think potentially like connecting with Tugsu and trying to figure out like, can we just like kind of approach it from a, hey, let's just like have a hermetic graph, use that as the cache key kind of thing, how well that would work.
Wait, do people actually have a plan for serializing the distributed constructs? Like anything that involves the process groups or the device meshes, can they be serialized logically? They represent some kind of notion of a connection and states and stuff.
So
yeah, so it's like, oh, sorry, go ahead.
I was just going to say that quickly. I actually think that we should like punt on all of this, like this distributed aspects, the higher order ops. We should like make this be like a addition, like a, I don't know, V2 of this cache. And for the V1 of this, let's just not support these.
Yeah, I don't think our discussion right now like changes how we're going to implement the cache. I think the way that we're going to do this is we're going to start with an allow list of well-behaved operators, and if operators want to be well-behaved and cacheable, then we're going to implement parts like incrementally into that. And that way, like we can do this work in parallel where like if the correct implementation for higher order ops is to just serialize all of them properly, then that means great, we can use that as the cache key here too. But key
Yeah.
part of this project will be like designing a good API so that operators can designate how they want to be cached or serialized or however you want to like specify that, like designing that part so that we can incrementally make progress. Because like obviously it's hard for someone like me who's designing this cache to know how every single operator works, and I'm not going to go and sign up for writing a serialization for every single operator in order to be able to do this. But I want to make it easy for anybody who wants to be able to cache their graphs with their operator to be able to do so.
Yeah, in that case, I definitely think that reach out to like Sherlock and Tugsu, because I think we have a similar problem with, say, like a higher order op and exportability, right? Like being able to serialize, where it's like we want to provide like a set of rules or an API by which it's like if you conform, you use these data types, you like you implement whatever endpoint, like you get compatibility with being exportable. And to me, it can be the same as having compatibility with caching, right? Like, and so people from a higher order author perspective, you don't have to like worry about caching or exportability as two separate concepts. It's just kind of the same thing that you implement once, and then it's well-defined, well-behaved, and our system can kind of bound it nicely. So I think that makes a lot of sense.
Ed, did you want to bring up?
Yeah, so this is like different. It's similar but different. Okay, so we need to be able to serialize pre-dispatch IR, right? So Jack Sao from Google is working on single-step graph capture. And one of the prerequisites he has for that is he needs Dynamo to trace out all the way to pre-dispatch IR before handing things off AOTAutograd. And there's a reason for this, which is that he needs access to the decompositions, because if you decompose an operator before calling the differentiable operator, that gives you safer backwards things, and Dynamo needs to know about them if it's going to take care of backward itself. And so basically, I'm not proposing that you actually like do the implementation plan like this, but in a universe where like we did this by default in Dynamo, then you would not be dealing with a torch and NN module graph. You would actually just be dealing with something like pre-dispatch IR, except decompositions had already been applied. And then you'd have less work to do. I mean, higher order ops you still need to like solve, but higher ops is going to just higher order ops. All of the torch star stuff would all be normalized to a further degree. That's it for
Okay,
me.
lots of comments here.
Yeah, I suspect I'm going to say the same thing Tuxie does. Like, to me, architecturally, it would be a very nice property if like the JITted path of Dynamo and export produce the same representation, which is pre-dispatch IR. And then like if you're writing a backend, it can kind of work for both, and you don't have to like figure out two different representations. Sort of which decomps we apply notwithstanding. So I kind of like it is basically what I don't know what the advantages or disadvantages are of producing this torchy graph out of Dynamo, but I wonder if
so
and this is something
one
that I brought up with
disadvantage
Brian.
is that it makes Dynamo more expensive, because the way it works today, Dynamo only just does a fake tensor prop and then it's done. And so Jack's thing, in order to get pre-dispatch, it has to run makeeffects in Dynamo to decompose it into a bunch of operators, which then go into the graph. So it sort of like makes AOTAutograd caching less good, because more work is being done in Dynamo at this point.
And so that's just a question
fun.
of like proxy tensor performance, basically, right?
Yeah, that's right.
Yeah. So Brian and I like vaguely discussed this, and we were trying to understand whether it was like in scope or not. It's obviously a much larger change to the like torch compile infrastructure. So yeah.
I was gonna say,
And
I
do you have
wonder
any
if that
thoughts on
all
that?
this,
Sorry.
like, how much does it actually matter in practice? We're like looking at the 3 bullets of like, or the 3 like types of categories of things in the Dynamo graph today, like torch, star, higher order, and then non-well behaved. It feels like 2 and 3 are the like thorny thing to solve, and then like caching well-behaved torch.star ops versus caching well-behaved pre-dispatch ops in my head, there
Well,
wouldn't
but
be a
hang on,
convergence.
so NN modules will show up in the graph
Yeah,
as well. So I don't know if you thought about that problem yet or not.
Are they, will they have custom like implementations that contain side tables that might affect this? Is that the problem here?
So we're only supposed to do this for well-known NN modules in PyTorch core library. So no, I guess. Yeah, probably is fine.
I mean, basically, I think if they do have that, then they fall in category 3, is I guess my
I think any hook or reparameterization even of on core module give them arbitrary behavior.
Yeah, but I think we're like not supposed to like plow them into the graph when they have hooks. I don't remember. Some folks were looking into why parameterization wasn't working with Dynamo last night. Was there anything useful from that investigation?
From what I remember, there was a PR. If there's a reparameterization, we just inline the inbuilt NN module.
Okay, that's what I was hoping. That makes sense. If you inline the NN module, then what I said doesn't apply, because you'll end up with ops. NYC?
no, yeah, I didn't need to raise it.
Michael?
Michael?
Yeah, I think to me, I don't think torch operators say and like pre-dispatch operators are that different. I think the main thing would be like if we can actually share a single representation, it makes it easier for like backend authors. I mean, you know, Jack's like single step Dynamo thing is like one example, right? Where we're like, oh yeah, it would be a lot easier as a backend if we only had sort of one more simple representation. But it, you know, there are always trade-offs involved in like determining what that one representation would be. So like the place where I'm like it would be nice is mostly from like a, hey, I'm writing a backend for this graph. Like it would be nice for it to look this way. Not from a like it would be easier to serialize or not easier to serialize. Although I will also claim that pre-dispatch IR has all the Python stuff stripped out, so by definition it will be easier to reason about, at least from a serialization perspective.
I guess I just want to bring up that I think that this work to serialize the pre-dispatch into pre-dispatch IR, it probably can be done either in parallel or separately from this caching work, because all we really need to do is design a way to say like, here's how we want to be cached, and you could implement that however you want. And if implementing that for a lot of the torch operators includes like making Dynamo do pre-dispatch IR, then we can definitely do that. It probably won't affect the actual implementation of the cache specifically. Obviously, it'd be nice if we did all of that work up front and then use that for the cache. But another way to do this is have the cache do its work, and when we want to be able to, you know, like for Dynamo to give pre-dispatch IR instead, like have that hook in just as the way that the caching is implemented for those operators. Does that make sense what I'm saying? Like as long as that AVI is a boundary, then we can separate those concerns, or does that?
Yeah, I think, I mean, I'm mostly bringing up like a differently scoped and like thing, so I agree with that.
All right, a few more questions on this, and then maybe we keep going. Yeah. So,
Horace?
Dispatch IR. Never mind.
Okay, my hand is raised, so I've got another thing, which is so there's been a lot of talk about like needing to design the API for making something cacheable, but do we really need an API? Like, why can't you just make a function and have a bunch of?
I mean, it could just be a function thing. When I say
just
an
be
API,
a function, have a bunch of if statements, because in particular you don't need an open universe, right? Higher ops, G-tensor stuff, they're all in PyTorch core, so like you don't need an open reg thing.
I would like to make it, I think like a function that does this is fine, as long as it makes it obvious that when you're introducing a new operator or you are doing some work in the space, that you have to update this function.
Yeah,
One
because it'll
problem with
error.
having
It won't cache, right?
I mean, will it error when a cache fails, or will it just not cache it?
Well, I mean, with
Yeah.
the cache will not work, and then
Yeah.
people will go,
Yeah.
why isn't the cache working? Well, I mean, you'll need stats
Mhm.
on this, right? But that's more on the metrics instrumentation side of things. I guess the one thing that like is problematic is allow and graph. That's OpenReg.
So
I don't know how load bearing allow and graph is.
So I think
Nice.
unless you force it, it will actually have a silent correctness bug. Because let's say that you added a new higher order operator that uses some, I don't know, site table or something. Unless you add this thing to make it so that like it is like unless you force it to implement like serialize, deserialize, what will happen is that it will serialize as if it's a normal operator, and then you will have like cache corruption and like silent.
No, concretely, my if statement basically looks for situations it knows are sound, does them, and then when it hits the end and like
It
you
fails,
still
yeah.
got this thing I don't know, it just was like dumb
Sure.
cache.
Yeah, I mean, when I say API, I'm not really I'm not saying like something we have to like publish to everybody. I just mean like some implementation that allows you to specify how your thing is written, and like how we actually implement that is kind of a detail, and like I'm happy to implement it as a big function with a bunch of ifs if you want me to. So but like I could also imagine it as implemented as like a method on higher order ops, or like I don't know, some object oriented thing. Like it doesn't really matter, right? In the end, it's like some big switch or a bunch of small switches, like essentially. So cool. The next two categories are a little bit simpler. The first is global state that AOTAutograd uses to do its work. So this basically, as I've been talking to Brian about this, so he's a little bit more familiar with it, but it's basically anything that affects our dispatch keys and any global variable that's used in the implementation of those dispatch keys. And from what we can tell, these are well known, so we can just list all of them, and those are going to be the ones that make it into the cache key. Again, another concern here for me is like, what if like someone changes how one of these things is implemented or adds a new feature and then adds a new global state? That will affect the cache key's correctness like instantly, and there isn't an easy way to be sound with these the same way that we can with FXREF. We can just ignore all operators, but we can't like figure out if there is a global piece of global state that is being used in some part of the AOT implementation. But if this is well known and we can just like list, and the number of them is small, I think that's fine. But Animesh?
If the global state changes, wouldn't Dynamo just recompile?
Yeah, I think in particular, like Dynamo has the same problem of like Dynamo needs to enumerate and guard on all the global state today. And so if we already have audited and done all that in Dynamo, we can just reuse that list.
Oh, so there are some global states where we should have guarded in Dynamo, but we don't.
Dynamo.
Well, we probably are guarding on all of them today, unless we're missing something. But
Well, for example, I have a bug report open how we don't look at torch dispatch mode.
yeah, so there's definitely yeah, and there's probably I feel like we don't guard on like weird functionalized global state that nobody ever uses. So there probably is some auditing work necessary, but.
Well, I think also the point is that even if it's guarded on Dynamo side, if this cache is going to be between processes or something, like that guard doesn't protect against this, and so these guards need to be in the cache key. Right.
I guess I'd also add that
Yeah.
like it is because you want to share these between processes, it is more important to get the guards correct because you're more likely to mess things up when you processes than same.
Okay. That's basically all the stuff that, I mean, it's not all the stuff. There's probably infinite other things that need to be in this cache key, but that's the overview of the cache key implementation. The second thing I want to talk about is what exactly we're going to serialize. So for this version, for the V1 of this product, I think after talking with folks, the best ways for us to do this is to serialize essentially the portions of the outputs of AOTAutograd that are then passed to the forward and backward compilers, along with any metadata that we can save to reconstruct the AOT module that AOTAutograd produces when you call like, you know, AOT underscore module or AOT underscore module simplified. So the parts that we're going to be caching here are like, after the partition function runs, we get a forward module and a backward module. Those two, plus any extra metadata that we can safely cache and not need to recompute. And then we use those to rewrap the compiled function into an AOT module, and then we return that on a cache hit. One question here is, why don't we just cache the entire AOT module, including all the parts that inductor can, like, after you've passed this inductor, you get a compiled thing, some executable. Why don't we just cache this entire thing serialize this entire thing into an AOT module and use that? There's a couple of concerns here that make it harder to implement if we do this. One is we actually don't know how to serialize an arbitrary executable as far as I can tell. The way FX Graph Cache does it is that it stores a handle to the PyCode cache and then recompiles portions of that. And so we'd have to figure out how to serialize an arbitrary executable. The second part is that inductor has guards that are not appearing in the dynamo space, where specific guards on behaviors that inductor cares about. One example of this is whether or not there are tensors with input sizes that are both above and below the int32 threshold. Inductor needs to have these dynamic guards that appear based on like the input. And because of that, we'd have to include all of that into the current cache heap. And we basically, in general, have to take anything that would affect any inductor behavior into the AOTAutograd cache in order to be able to do that. So that's going to be expensive. So in the first version of this, we're just going to make it single layer, where it caches the part that AOTAutograd, like an FX graph that AOTAutograd produces, and basically just Python code at that point. And that makes it a lot easier to serialize. And wrapping doesn't, from our tests, doesn't seem like it takes a very long time. So hopefully that won't be too expensive. Obviously, a concern here that we have is that, like, I'll draw a little diagram here, where like today we have XF graph cache and it goes into the PyCode cache and it returns an executable and does stuff. OS is going to make it so that FX graph cache here, which is on disk today, is distributed, and make it also interact with the Triton cache, which is already today distributed. And we're going to add this AOTAutograd cache on disk initially, and then maybe distributed later. That basically is an extra single layer on top of these two caches. So like anyone staring at this will be like, well, we have 3 different caches and they're all distributed, and we're calculating 3 different cache keys and doing 3 round trips to memcache to be able to like calculate this. And that seems like not great design. So in the future, I think it would be helpful for us to think about like making some sort of universal cache key that works for all 3 of these caches, so that you go 1 round trip to this cache and it gives you back everything you need. That's not going to be within the scope of at least this first version of what we're doing, because again, calculating this cache key is hard enough as it is, and calculating it based on all of the extra portions will be difficult and probably involve a lot of different other moving parts. But that's just a call out to the future that I want to talk about. Any questions about that? Ed?
I'm not convinced. So try to convince me that implementing a 2-level cache, including once you've gotten out the cache products, you have to feed them into the inductor cache and then get out the compiled products and then wrap it all back into an actual live example. Convince me that this is actually simpler than the like eventual model for the unified cache, which is I do an AOTAutograd lookup, I get a thing, and then I run the thing, and I'm done.
I think it is a simpler point to get to from where we are today, I guess, because today we have a FX graph hash that we think is correct or is sound, and a bunch of extra, like the way the FX graph cache works today is that it has a bunch of extra guards and things that are part of the way that it does the thing, where essentially when there's a cache hit, it needs to evaluate a dynamic guard that's essentially just arbitrary Python
Well, so I
Uh,
mean, Ooze was just telling me about how they were going to get rid of this.
Well, the goal is to get rid of that for sure.
Wait. To be clear, I wanted to get rid of it, but you said don't get rid of it. So I don't know about that.
Well, talking to others about this, I think like he and I actually discussed this a lot, which is it simpler to start from like the biggest picture version of this? And I think that the conclusion we came to is that making it modular at the start makes it easier for each of us for us to make good incremental progress, and it doesn't make it harder for us to combine them later. And to me, at least, it makes sense for each part of the like Dynamo inductor AUTOgrad like pipeline to like understand its own API and then understand like how to cache its own products than it is for us to immediately do the more ambitious project of like figuring out everything that AOTAutograd needs in order to be able to cache no matter which backward compiler it uses. I mean, obviously, like we could just support only the inductor one, but like, and also concern itself with all of the other moving parts of this, and like the context needed to be able to do such a change, I think, is bigger, especially with the existing state today. But do you have any extra?
Yeah. So I think the big part here is that like testing. If we were to do this like in one entire cache as opposed to doing this modular, it will be very difficult to actually make sure that like everything we have is correct. And having the modularity or like having this modular behavior enables us to test individual parts for their own merit, and also allow us to like move them from like, I don't know, to the in disk to remote, like all on their own. And ultimately, I do think that like we should have them in the one cache, because otherwise we will have to like look up 3 different cache keys. We will have to like fetch 3 different times from memcache or like whatever we use. So it will introduce like more points of failure eventually. But for the first run, I think it's just in order to make the testing and productionalizing this simple, this modular behavior is going to be a lot easier to handle.
Reason about, yeah.
Yeah.
James, you have a testing section at the top. Tell us about the testing strategy.
I have not written one up yet about this, but I think
Well,
that
tell us what your best guess on how you're going to test this is.
yeah, I think that like we have a lot of existing like prior art in like testing like the FX graph cache and stuff, but essentially I think that the structure here is that as long as because we know that the set of inputs is because the set of inputs is known, and as long as we define well the cache key, and the set of outputs is known as a set of
Actually,
FX
we want to
graphs.
say, tell us how the
Oh.
testing for the inductor cache works today.
So there's a set of unit tests called test code cache, and I think the way that it's implemented is that you can like we like give it a bunch of examples of FX graphs, and then it like we expect some sets of outputs from it. And the types of examples that I think it's a set of unit tests and the basic expect behavior. I'm not 100% sure if there is more complicated testing than that. Essentially, it's just a set of inputs and outputs. And the nice thing is that I think because it focuses itself on a known set of inputs and outputs, you can write it in essentially as a set of unit tests in that way. And hopefully we can do that with AOTAutograd cache too. I do think that like part of this is also, besides just testing, is observability, in the sense that we should also have a way to dump, given any input FX graph, even in production or whatever, the set of things that go into the cache key, and also any sets of reasons why it can't go into the cache, for example. And we could put that into TL parts, we can put that into logging as well. So that's what I'm thinking about, which is like good set of unit tests, and then once it's ready, we put it into a job, have it log when it can't cache somewhere, and then we can look at those logs and then fix. And obviously we can stare at it in the beginning, so we can avoid having to immediately log, but like we can log for edge cases in that way, where like if it can't cache, we just, we have something in Scuba somewhere, and we can see the reasons for that and fix it that way. So, does that make sense as a testing plan? But like,
I was expecting to hear something about taking all of our existing Dynamo test cases and running them with a cache on or something like that. Isn't that what we do with the inductor cache? Like, isn't that how Sam was
Do we
finding
do that?
lots of-
Don't think, I think we talked about it, but I don't think we ever implemented that. Because I think the discussion was that like if we were to do that, the test would take significantly longer and we don't have the CI capacity to actually do that, right?
I mean, it'd be kind
So
of
I
nice to
thought
just
Sam
do
was
offhand
doing-
anyway. Maybe we should just do that, even if we don't put it as like a CI test.
I thought Sam was doing something with the testing that was like helping him find like key things that were missing. Am I hallucinating this?
I think he has done that himself and run all the tests, but I don't know if it's committed to CI currently.
So it's an offline, okay, offline.
I think
That makes sense.
That's a really good idea. I'm down to do that though.
So perhaps we should just like find a single like a file of tests and then just like add that double run on the CI for that one. So that like we don't increase the CI time by too much, but we still have somewhat testing.
If it's gonna be hard to put it into CI, are there ways that we can have it run only on risky diffs? I don't know how to like get that to be the system that we want it to be, but
I think
Well, we have a nightly periodic tests, like that's an option.
for a little more context, I think he was adding like test isolation with like adding fresh inductor cache to all the tests, and then from there that would make it possible to run the test twice, but currently if you don't have test isolation, like because of symbolic shapes, if you have like multiple compilations for different symbolic shapes, like if the tests are run non-deterministically, it's also like non-deterministic which symbolic shape FX graph cache you pick up. So I think he was currently adding test isolation, and then from there it'd be possible to run twice, but makes sense.
I can talk to him offline about this and like see what we can do on our end too. Okay, I think that's all I had. Yeah. Any other questions?
My parting thought is it should be possible to serialize the callable and inductor. This seems like a very reasonable thing to want.
You mean the inductor callable?
Yeah.
That would simplify a lot of things.
Like this just seems like a project that someone could work on, independent of it.
If you can serialize that callable, is it therefore easy to serialize any Python wrapper around that callable by definition, or is it like we have to implement a
No,
serialization
every
for each
wrapper
one?
has to be serializable, but
Yeah, so
but
then-
the point is that once you have the inductor callable serializable, the rest of it is like AOTAutograd's responsibility. So like as in
Right.
it's your responsibility to make those wrappers serializable.
Yeah, and theoretically serializing that, which is just Python, should be easier.
So
Anyway,
is your suggestion then to serialize the callable so that the inductor cache is just a file cache and like it has everything in it that it needs, as opposed to doing like more PyCache loads and stuff?
Let me think.
I think Ed's goal is to just make one cache key for everything.
Yeah, so I want one cache key for everything. So like, obviously like I'm willing to abort and change my plan if things are terrible. But like the first thing to investigate in this line of inquiry is, can I make the inductor callable that gets returned from CompileFX?
Yeah,
internet?
I mean, I think we should just like do I don't know, separation of concerns and like try to find the small items. And like the first things that we would need to deal with in order to have one cache key is to get rid of this like inductor generating more dynamic, like caring about that fact that inductor generates more guards, and also around this like bytecode cache. So if we can solve both of those problems, then we probably don't have that many obstacles in our way.
Yeah, at that point, I think you could just have one cache key for everything. Well, how does the Triton cache key get calculated, and does that get affected by any of this?
So the problem with the Triton one here is that like with local caches, when you have like the Triton artifacts are already compiled, so they're already on your machine. However, with the remote one, we would have the Triton compile stuff will have to be fetched from Memcache too, but we can just make it as like a follow-on step where we just download that additionally from Memcache.
As in, is computing the cache key for the Triton cache something that will be hard to add to the AOTAutograd level? Like, does Triton have weird guards or anything that would affect that?
No, the Triton cache, like we could even generate the Triton cache key inside AUTOgrad. Like doesn't matter. It's very straightforward.
Okay.
It just does a
It doesn't
SHA-1
depend on the inductor output at all?
Oh no. So it does a SHA-1 of the kernel inductor generates. So if we have the access, if we have access to the kernel, then we can just SHA it as well.
Okay, so we do need to then store the
So
SHA-1 of
first,
the, yeah, when we first do it, we'll just store that part. Yeah, that makes
Yes.
sense. Okay.
or not SHA-1, SHA-256, but whatever.
Okay, thank you. Do we have a Joel here?
I'm here.
Okay, well, it's not too much time, but if you can give us like a condensed like stuff that would be useful to talk about in this meeting, that's my suggestion.
Yeah, so we did talk with Brian some, but it'd be good to get some other opinions. I think one of the main things that's blocking us is the issue that Christian mentioned. So I'll cover some context real quick. Let me share. Okay, so the background here is that for SDPA, especially the performant kernels like Flash and memory efficient, we need to pass a max sequence length and min sequence length. And computing this incurs a GPU sync, and we don't want to compute it across all intermediates. So we kind of cache it and pass that cache along through isotensor operations. And then the issue here is kind of pointing out that this max sequence length is, well, the constant for that is baked into the graph here. So, and we're not getting recompiles. So there's a correctness issue on recompiling. And then there's like also a dynamic shapes issue because we don't want to ideally recompile every time the max sequence length changes. Does this framing make sense here? Okay.
Let me see if I understood. So what I heard was two things. So one is that there's a missing guard, right? So if we had guard in on max seq length, at minimum we would have recompiled a lot, and like recompiling a lot is bad, but that would have helped. And the second problem is you want max seq length to be like dynamic by default, so you don't actually recompile.
Yeah, that's exactly right. So I think Brian mentioned that there's a PR out to properly guard on subclass context, and this stuff is part of the context, so that will address the correctness.
Okay, so it sounds like part one is fine. So part two is the problem, is that right?
Yes.
Okay, so tell us about what your current thinking is.
Yeah, so I think if we want to take the approach we've been taking where we solve this for the general subclass issue, it would be add dynamic shape support for subclass attributes rather than treating them as constant by default here. I think Brian probably has more details on what this looks like, but it's sounds like it takes a little while, several weeks to accomplish.
Yeah, I think that's right. I guess to me, it kind of feels like in full generality. So we have like a constraint today on tensor subclasses with compile, which is to work with compile, you have to have a wrapper tensor subclass that holds inner tensors, and your wrapper tensor subclass must consist of inner tensors and constant metadata. And is the like constant metadata a reasonable constraint? This seems like the first instance where we're saying it's maybe unreasonable. And I guess meta point is that this particular issue feels like a perf issue, and solving the perf issue via like symbolic metadata feels like one implementation of solving the proof issue, but it feels like there's a bunch of like options on the table for solving performance problems like this.
Yeah, I
Can
think
I propose a very horrible workaround? So instead of max seek length being an attribute, which is static under the current subclass design, why don't you just have a 0-element tensor that has max seek length as its size? Does this solve your problem? Question mark.
does this solve our problem? If that, so you're saying store as a subclass attribute, a 0 or
No. So tensors can be dynamic,
yeah.
but attributes can't be, right? You got a int attribute that you're like, man, I would really like this to be dynamic. So I'm like, well, any int attribute can be stored in a 0-element tensor. You just have a tensor and its size is 0, comma, your int. And this doesn't take any space because of the 0, and you can pull out the integer later from the tensor, which will be symbolic.
I would potentially expect that to work if it's a CPU tensor, I guess, and you then still call .item when you launch.
No,
the
it doesn't
kernel.
matter if it's a CPU or a CUDA tensor, because
No, but I'm
there's
saying
no
like
elements.
if you want to emulate it,
I'm
a
not calling
dynamic
item
integer,
on it.
how are you going to pass it into the kernel so that the kernel doesn't have to read it from global memory? Like how
It's the
are you going to make it
size, so I just read off what the size is.
the size?
Oh,
Yeah, like as I said, the tensor is a 0 by n tensor, like it's a 2D tensor, where one of the
Oh.
dimensions is size 0.
You're going to store the integers as part of the sizes, and okay.
Yeah, as far as the size, because sizes
Okay,
on
I see. So
tensors
we're
can be
allocating
dynamic.
a whole tensor struct to store one integer.
Yeah, I know, it's terrible for
no,
Igor
but like
mode,
that
like-
works. That works.
this is fun. Yeah, I think I
Yeah,
like
that's
the
a
idea.
pretty good idea.
I think morally I hate this.
It won't scale if we have a lot of them. It will work for one.
Yeah, I mean we're kind of stuck between two solutions right now, besides this one, that are like not fast. So general dynamic shape support for subclass attributes, or making this like a more global thing as we move the cache out for the nested int revamp. And that's like, that takes time too. So I'm definitely willing to try this little size hackery.
You could actually use it for as many attributes as you wanted. Just make the tensor n-dimensional.
No, I think on CUDA it's limited to 25.
Oh,
Sorry,
okay,
Basil.
okay. Yeah, I just wanted to make it as morally filthy as possible.
So like, if you do want to solve this first class, the place I would start is just when I have a just regular PyTorch2, no tensor subclasses involved, and I have an integer input, there's no way to tell Torch compile, hey, please immediately make this integer input dynamic. Actually, like Dynamo has all of the like inner machinery needed to do this. We just like don't have any API service for doing it. So that's the first thing that I would solve. Probably you do it by having a class that contains an int in it, and then Dynamo knows, oh, when I see an int inside this class, I do something different than when I see an int just hanging out. Once you've done that, then the next step is what the heck you're going to do with the subclass machinery. And I don't know, I guess we'll have 3 classes of things: tensors, these int box thingies, and then static metadata. Where the int box thingies are basically like tensors, except they just don't have any data. I don't know, it seems like the same thing, just, you know, you put more paint on the shed at this point.
This is like only semi-related, but like making sure I understand the proof issue that we were talking about. Like the whole reason you need this is because it's expensive to recompute this int in the middle of the graph every time you want to call the kernel, right? And is the other option, we say like you need this cache for eager perf, but then when you're in compile worlds, like we'll have a graph. Like suppose you didn't have the cache at all and you're using torch.compile, then we'll end up with a graph that looks like doing the slow compute of the min and max every time we call flash attention or whatever, and an inductor could like CSC that or something. That would be like equivalent to having the cache.
Yeah.
So concretely, it would be like cache as eager optimization, and then like don't cache when you're using compile. That feels like it has downsides because you're like branching on compile behavior, but
Yeah, I mean, I think conceptually moving performance decisions to the compiler makes sense. Just we have to get the guarantee that that would happen.
But question, can't the backseek length be passed in as an input? So there wouldn't even be a computation step in some cases.
so my understanding is the only reason you're passing it as an input is because you want to do the caching. Is that right? Or are the people like actually passing the minimax as an input like separate from the performance stuff?
Yeah, just for performance, and the model use cases we're looking at now just pass a static large enough max length to kind of get around this whole dynamic issue.
Oh, I guess that means you have like different inputs to the thing if you're using compile or not, which is kind of bad.
Yeah, yeah.
So concretely, if my compile region is taking in a nested jagged tensor as input, potentially the user could have pre-computed it for me, or I need to compute it inside the graph. If it's pre-computed for me, then I just want to use the pre-computed thing.
Yes.
If it's inside the graph, then I'd like to compute it once and then use that computation for all my functions.
That's right. And I think there are cases where they have access to this pre-computed value in a faster way than we could do it in the graph.
Okay, well, are we gonna call the meeting 4 minutes early? Anything else? All right, well, thank you, everyone. See you all next week.
See ya.